At RES4Africa, we stand for Africa. We believe in its huge potential. We believe in its innate energy. We believe in its growth. And we believe that all it needs is an enabling environment for its full development. At RES4Africa, we care for Africa. That's why we believe that clean energy is the only way to go, because renewables mean more affordability. Because renewables mean more jobs. Because renewables mean more value. Because renewables mean more resilience, social justice, and health. At RES4Africa, we join for Africa, a unique blend of expertise along the whole value chain of renewables, joining forces to accelerate the transition towards a sustainable and inclusive future. At RES4Africa, we innovate for Africa. We constantly look for new, improved energy solutions to provide not just clean and powerful electricity, but also cutting-edge and reliable plants, electrical grids that guarantee quality and stability through digitalization and storage. At RES4Africa, we act for Africa. We promote dialogue between governments and private players to define conscious, long-term policies, encouraging adequate investments. We share know-how with all stakeholders to promote the full development of Africa together. We train locals on the field to share our expertise and make them owners of their energy. And we never, ever stop looking for new and win-win business models made of African DNA. We are RES4Africa. Our mission is to build a better future through better energy. In Africa, with Africa, for Africa.
Good morning everybody. Welcome to the fourth session of the RES4Africa Labs, the new format that RES4Africa has launched this year to touch specific topics in one for each webinar dedicated to the most important and crucial aspect of renewable energy and Africa. So today, the topic is probably the most important, focusing on the principal enabler of renewable energy, that is the electrical system, the electrical grids. And we will do a journey inside the grids of the future, the grids that are able to host high levels of renewable energy, that are fully digitalized, that are smart grids. And for doing this, we have three special speakers that will touch different aspects of this very, very important topic. We will start with Silvia Corigliani from CESI, that is one of the members of RES4Africa. CESI is a world-leading technical consulting and engineering company that works at global level in all the aspects related to the electricity. And Silvia will touch mainly all the aspects related to which is the impact and which are the actions when the renewable energy inside the grid richest level of penetration that can impose a different architecture and new components inside the grid. After Silvia, we will have the second speaker of today, that is Mena Testa, that is she's from Energrids, and will go more in deep on the aspects related to digitalization inside the distribution grids. And finally, we will have Darwin Pala from RES4AFRICA, that is a unit inside RES4AFRICA dedicated to the grids, and he will tell us which is the reason of this unit inside RES4AFRICA, and which is the vision of RES4AFRICA on those topics. So I don't lose other time, and let's start with the first speakers. So Silvia, the floor is yours, and let's start with the first topic.
Okay, thank you very much, Fabrizio. I hope you can hear me well. I'm happy to introduce this session on the topic of technical flexibility solutions for grids with high VRES penetration. So let's start. Next slide, please. Okay, first of all, I want to introduce you to the technical challenges related to the integration of renewables into the grid. First of all, we are speaking about variable renewable energy sources. So we are adding the V in front of RES because we are speaking about mainly solar, wind energy, and in some way run-of-river hydropower system, but mainly solar and wind energy, for which we have no control on the primary energy source. So we are leaving aside for this specific presentation biomass and big hydropower plants that are controllable and predictable. So when speaking about variable renewable energy sources, we have different challenges that can be categorized into these three different colored blocks. The first category of challenges is related to the nature of the primary source of energy of these renewables. The primary source is continuously fluctuating. We can imagine the clouds for the solar energy. We can imagine the wind that continuously changes during time. And those fluctuations are also uncertain. So we can somehow forecast the weather conditions, but we never have 100% accuracy in the prediction. So those fluctuations are hard to predict. Also, these renewables have a low capacity factor. Capacity factor means the amount of energy they can produce during a year with respect to the maximum amount they could produce if they were producing at their maximum power over time. For solar, we are speaking about 20%, for wind 40%. So basically, we are installing plants that are not available during all the year. Solar during night has zero energy production. And also they are very location specific. So especially wind, we cannot install wind where we want, where the grid is present, but we need to select those areas where wind is very strong, typically offshore or on some ridges. So those are also areas that are often far from the main load centers. Also, if we speak about solar, we can imagine the desert. We have a lot of solar availability, but super far from load center. We have challenges related to the type of technology. So those technologies are connected to power converters because they are mainly DC sources. So we have a different type of technology. Instead of synchronous machines that were traditionally connected to the power system, we have power electronics that reduce the system inertia, that could have an impact on the power quality in terms, for example, of harmonics, that have a different fault behavior, so they don't inherently sustain, for example, the short circuit current. And they have different capability in terms of reactive power. So you can imagine that regulation and power system operation will need to take into account these technological changes. And also, renewables are often connected, especially PV, at the distribution level. And this is something new for power systems, where traditionally the production was more centralized, was coming, we were having one-way flows from the transmission to the distribution and to the loads. Now we are having reverse flows, and you can imagine this could have impacts on the protections. It could have impact on the visibility, so a difficulty in managing all these new sources if we don't have proper monitoring and metering systems. And it may also affect the capability of properly planning the distribution grid that in the past needed only to take into account for the growth in the load, in the demand consumption. But now distribution planners need also to understand which will be the hosting capacity, that is the capacity to host renewables in their system. So we have several challenges, and we need to understand which could be the solutions to put in place in order to avoid what we will see in the next slide. That is the risk of RES curtailment. So of course, when we have so many problems, so many challenges, and we cannot deal with them, the easiest thing is to curtail, that is to cut the production from renewables. And this may also be due to two main problems: the impossibility to balance demand and generation in the system. So if we have moments of overgeneration and the system is not able to respond flexibly enough to this overgeneration, well, we will need to curtail renewable. And the other main reason for curtailment is that we have network constraints, so we have congestions and lines that are not able to transport all this power generated by renewables, so we will need again to curtail because of lack of adequate grid infrastructure. Next slide, please. Here on the graph, you can see what happens when increasing the penetration of RES capacity. So you can see this is an example of a small power system. The capacity was increasing from a 5% to 28% of penetration. And at the beginning, the curtailment was very low, was contained between 5%. But at some point, when the penetration of renewables increased too much, the curtailment increased exponentially. And so it means there is a maximum feasible penetration level for the integration of non-programmable VRES, above which the curtailment is so high that it doesn't make sense to install more renewables if we don't take countermeasurements in order to integrate these renewables. And this penetration level depends a lot on the characteristic of the system. The more the system is interconnected, the more the generation plants are flexible, the more storage systems are present, the more the penetration level is higher. More system will have, for example, more problems in this sense. Next slide, please. Here is an example, actually, is what was happening in Italy. So from 2009 up to 2019, the wind penetration in the Italian system increased. So more and more wind turbines were installed. The total capacity was installed, and together with the total capacity, the wind generation was increasing. You can see from 6,000 gigawatt hours to 17,000 gigawatt hours of energy produced during the year. But what was happening at the beginning is that of this amount of generation, the 10% was curtailed, because wind in Italy is installed in the southern part of Italy, and the majority of the loads are in the north of Italy. So the lines were not able to transport all this huge amount of energy from the south to the north, and the energy was simply curtailed. Then wind was continuously being installed, but curtailment was decreasing, even though the generation from wind was continuously increasing. Why they were able to do so, how they were able to do so, so to reduce up to 1% and 2%. Well, they put in place different countermeasurements. They reinforced the grid on these north-south corridors, and increase the flexibility of the traditional power plants to balance the production of the wind. Also, storage plants, pump storage in Italy is very important, start to operate differently and to help compensate the overproduction from wind. So this is to demonstrate that it's possible to increase the penetration of renewables without increasing the curtailments if you take the proper countermeasures. Next slide, please. So what to do is, of course, as always, a compromise. RES curtailment as a cost, because basically we are installing something that we are not using, and we are losing free energy, that is the green power. Also, the majority of the regulations, for example, also in Italy, compensate the energy curtailed. So if the TSO, if Terna needs to cut the production of renewables, it needs to, in any case, pay for that energy that is not being sold. So it's a cost. But also the solutions to implement are costly if we are speaking about infrastructure, storage systems, increasing flexibility of plants. So what to do is a compromise to choose which is the most convenient thing to do. Generally, curtailment is accepted up to a certain level, that is around 2–5%. After that, some countermeasurements should be put into place. Next slide. Here you have an image representing what does it mean, the risk of overgeneration. So we have the blue curve, that is the load, and we are speaking of net load when we consider the fact that the load is decreased thanks to the production of renewables. And the problem is that if this net load is very low, and if we have constraints related, for example, to the import power that was already paid and need to be dispatched, or constraints related to the minimum amount of dispatchable sources, we may have cases of overgeneration. That is the green curve. Basically, the generation cannot be equal to the load, but it will be higher. A solution in this case is represented by the blue curve, where pump systems are absorbing energy during the moment of overgeneration, decreasing in this way the overgeneration that at the end translates into curtailment. Next slide, please. Something to keep in mind is also the characteristic curve of the net load when renewable penetration increases. What happens is, here is an example in Italy, is that basically, especially during moments of low load, for example, in Italy, Sunday or the middle season, where we don't have air conditioning, we don't have heating systems, so we have low load. The minimum load may be very, very low, and may not, the minimum left load will be very, very low and may not respect the reserve constraints on the system. And also, we may have very steep ramps if we have a lot of PV production, for example, when in the night the PV stops producing. So the plants basically will be switched off in order to account for that moment in which load is basically zero, and they will have to start producing very fast to compensate this peak in the night. Next slide, please. So here you can see that to store a system may be very useful for that moment in which the load is very low. We will need plants able to respond to those steep ramps, and here you have some numbers of what may happen in terms of ramping. But also, what may also be interesting is that it may be interesting to smoothen up the curve of the RES generation, the green, the gray curve here, that is so steep because it's mainly due by PV. But if we, for example, install wind and PV in the same time, that gray curve will be flatter. So it means that the net load will not be will not have those steep ramps, but will be smoother. So flattening the RES generation curve is also something that may help the system. How to do this? to install different type of renewables in the same moment. So not focusing only on PV or on wind, but balancing them out. Next slide, please. And here you have, let's say, a summary of what we have been saying before. So to comply with the risk of generation, we need to increase the flexibility of the plant. We would need new connections to export overproduction to new countries. So building new big links to export all this overproduction, build new storage system, increase the system reserve, and diversify the renewable energy sources. Next slide, please. Here is an example of what we intend with increasing the flexibility of the plants. It means, for example, shortening the startup time and lowering the startup cost. Decreasing the minimum load of the plants and improving the partial load efficiency, because the problem is that conventional plants have low partial load efficiency. So improving this may help reduce, being able to reduce the minimum load. Increasing the ramp rate and having shorter minimum uptime and runtime. Now, I will not present you all this table, but here you have some numbers to see with flexibilization intervention on existing plants, which reduction of all this quantity we can reach, and is very relevant. So we can even half out the startup time of units with proper intervention. Next slide, please. Here you have an example for a combined cycle gas power plant. The curve shows you the starting of the plant. So you see there is some startup time, and then we have a ramp in which the production is increasing up to the nominal power. If we consider new type of combined cycle power plants, they may have a parallel startup of the steam and of the gas turbine. So they may decrease the startup time a lot, and also they may be also operated as open cycle gas turbines. So in case where we need very fast response or to reduce the output a lot in a very fast way, we could bypass all the steam cycle, that is the slowest cycle, and use only the gas cycle to respond to peaks and ramps. Of course, this is decreasing the efficiency of the plant. So once more is a compromise, because we are doing this to include more renewables, but then we are operating the plant at a low efficiency. So we are actually emitting more CO2. So as always, this should be thought of as a compromise to understand which is the best operation of the plant. Next slide, please. The other, you remember I was telling you, one problem is overgeneration related to flexibility, but one problem is also related to local congestions, grid congestions. Of course, the first aspect to reduce grid congestions due to the fact that renewables are installed where the renewable source is to construct new lines, build new capacity, and here you have the numbers for ENTSO-E, the European Network of Transmission Operators, that have plans up to 2040 of installing more than 88 gigawatts of new transmission capacity, and including also storage system. Also storage may be used to relieve congestion on the lines, because it could absorb on one side and release on the other side. So if we put storage systems on two sides of the same lines, it may help to make the power flow only where the line, when the line is not congested. So this is the reason why also 41 gigawatts of storage will be installed, and why they will enable to release some congestion on the grid. Next slide. Apart from the planning, sorry, here you have an example of Germany, where basically renewables are in the north, especially wind, onshore and offshore wind we have in the north, and the load is in the center together with PV. They are planning to build 3 new HDC links to transport power from the north to the center. Next slide, please. Another interesting aspect is, okay, instead of building new infrastructure, we could improve the operation of the infrastructure we already have. You may know that transmission lines have a thermal line rating. That is, I can make flow a maximum amount of current on the line, because if I overcome the thermal limits, the conductor will have a temperature that is too high, and it will have a sag that is so wide that it will not respect the minimum clearance with the ground. It will cause short circuits. And normally this rating is done in a static way, so according to the worst possible weather condition in a certain area. In this way, basically, when the weather conditions are better than the worst, we are underutilizing the line, because the planning was done with a conservative approach. Next slide. So during operation, what is being done already in Belgium, in France, and more system operators are implementing, is the dynamic line rating. So let's measure real time, which are the real conditions on the line. Is there wind? Because wind is cooling the line, so the temperature may be lower than what expected, than the worst condition. Is it night? Is the air temperature very low? In all these conditions, probably I can pass I can make on the line flow a current that is higher than the static rating capacity. And with this dynamic line rating, that implies putting sensors on the line, having advanced computational techniques for computing the actual capacity of the line, and having also weather forecast to understand which will be the weather condition, we will be able, as you see in the graph, to make on the line flow a lot more of current, and this may help in moments of congestion to better dispatch the power plants. So we may dispatch more on congested line than what we expected. And this is very interesting also for wind turbines that actually produce a lot when there is wind. So when you have a lot of production of wind, and you know that the line is cooler thanks to the wind cooling effect, actually you can exploit more those lines, and you can flow more wind power on those lines. So it's very interesting for this contemporaneity with the wind production. Next slide, please. Other aspect that will be touched in the following presentation, so I'm not telling you much about this, is the fact that distribution system operators will be active agents in the we need to be active agents in the planning of the flexibility on the grid and in dispatching. They may help the TSO actually if they are enabled by proper regulatory framework. They may help in providing flexibility services to the grid when they, for example, aggregate all those distributed energy resources in agents that are providers of ancillary services, where they are able to control the load, where they are able to control the DR, when there is proper, when there are proper platforms for exchanging data between DSO and TSO. So there will be a new and more important role for distribution system operators in these new environments. Next slide, please. Also, it will be important to improve the control functions on the inverters. So also inverters will not have to be only passive users of the grid, but new advanced functionalities will be needed. For example, virtual inertia. We said that in the past, synchronous generators were connected to the grid, and they were able to intrinsically provide inertia. So if there was a power imbalance and a frequency imbalance in the system, they were instantaneously reacting to the frequency imbalance and bringing the system back to equilibrium in a very fast way. Virtual inertia control will mean the same. So inverters that are able to react to frequency imbalances, providing power and regulating the power output in a very fast moment. And these may also be enabled by BEST, provided with virtual inertia, or also what is called fast frequency control. Those new grid forming controls may entail also short circuit current contribution, so inverters that supply short circuit currents during faults, inverters that are able to black start So when there is no current in the system, they are able in any case to start again. And this is already implemented in inverters that are working in microgrids, where they actually need to sustain those microgrids based on renewables. So it's something that is already available, but is not so diffused. So it will be important also in the grid codes and in the regulation to force those new units to supply those services thanks to new advanced controls. Next slide, please. Demand side management is could be another source of flexibility. We can think about vehicle to grid solutions. So when vehicles, new electric vehicles are charged and discharged according to the needs of the grid. Hydrogen, that we could produce hydrogen where we have surplus of energy. We could imagine industrial loads that can detach and control their power according to the market signals. We could even imagine smart homes or final customers that switch on and off their appliances at the need. So demand could help, in addition to the conventional generation, to flexibly adapt to the system that continuously changes. And also this is something that is already in place, especially industrial customers already participate to the demand side response. Next slide, please. Finally, let's say this is something we were speaking about, the importance of creating new interconnections, and these new interconnections may be HVDC links able to transport a lot of power over very long distances. And when we are speaking about offshore wind, this is something happening especially in the northern part of Europe, in the North Sea and Baltic Sea. We will have, the plan is to install more and more offshore wind generation. And in order to better integrate all these generation into the grids, the idea is let's not connect each plant with a single link to the mainland, but let's try to create mesh grids, offshore mesh grids for these offshore systems, so that we can exploit more the congestion on the lines. We can exploit better and exchange power to better exploit all the lines, and we could have more security of supply. So if one line has a fault, the power produced by offshore energy can flow into other direction to the mainland. This was something. This is something that is still not in place, but for the future we will be there. Next slide, please. So we arrived at the end of this presentation, and here we can summarize all what we are saying. So the importance to ensure flexibility of conventional power plants in terms of upward and downward gradients, reduce technical minimum number of hours for the in-service and shutdown, ensure adequate transmission and distribution infrastructure not to have bottlenecks, the development of new interconnection for the integration of new VRES capacity. Next slide. They had forecast, we didn't speak about this, but of course, the more we are able to forecast the renewable generation, the better will be, and the easiest will be to manage it in real time. Energy storage system, the coordination between TSO and DSO, the adoption of additional components on the grid. We didn't speak about this, but synchronous compensators, for example, FACTS devices, grid forming inverters, and mesh grid offshore and HVDC links for VRES integration. So I finished my presentation. I hope it was clear, even if I went a bit fast, but it was a pleasure for me, and have a nice day. Thank you. Thank you, Fabrizio.
Thank you, Silvia. Thank you, Silvia, especially for the capacity to resume, to synthesize such a long story in few minutes. That is, I imagine, is very, very complex, and because the topic is quite complex. But I would say, I would summarize in the sense that the final message is a positive message, in the sense that all the actions needed to allow a very high penetration of renewable energy are available, And so the only problem, of course, is to choose the best ones and to put in place together on time in order to avoid in the future curtailments and limitation in the development of renewables. So thank you again. And now, as we focused until now on transmission grid, now let's pass with Mena Testa to the role of the distribution grid. Please, Mena, the floor is yours.
Thank you very much, Fabrizio, and hi everyone. Thank you, RES4AFRICA, for this invitation. It's a pleasure to be here with you today. In Enel Grids, I'm in charge for market analysis with the focus on regulation, especially. Next slide, please. I think all of you know Enel Group, and Enel Grids is the business line in charge for distribution of electricity, with more than 2 million kilometers of distribution networks and to more than 73 million of end users. Enel operates as a distributor in Europe, as main operator in Italy, Spain, and Romania, and we are also in the capital and main city in Latin America. So the point of view has the benefit from different contexts and different environment in terms of characteristic of the electricity system. What are you going to see? Next slide, please. In this module, in this short webinar, we try to summarize the contents of the module that will be available for you. And we will start from an higher point of view compared to what Silvia explained so far. So we'll have a look to the global context and the global trends in terms of energy transition, especially looking at which of these trends are affecting the role of distributor of electricity. Why it is relevant? It is relevant because we have seen how the distribution grid will be really impacted and really key to enable the transition. So we will go to see which should be the feature, the characteristics that the grids should have to be the real facilitator and accelerator probably for the transition. And we will go through these to see the part of resilience of the grid, the digitalization, the flexibility, looking also to the sustainability, because all this evolution of the grids should look always to be sustainable grids. So next slide. I think we can skip the agenda and we can go directly to the next slide. Thank you very much. Looking at the context. I try to be very quick on that, but I have really 3 pages to focus on main trends. Okay, so all of us are aware of the decarbonization trends. It's more than a trend. I would say it's an obligation that we should have. I highlight in these pages the point of view from International Energy Agency. In the most ambitious scenario they develop within their World Energy Outlook, the recent one in 2022, November 2022, the net zero emission scenarios. So few words on renewable part, focus on solar photovoltaic and wind. The figures are pretty clear, I would say. We see that in terms of terawatt of installed capacity at global level, we will see an increase from 1.5 terawatt hour today in 2020, let's see, to 23 in 2050. So the deployment is accelerating in all scenarios, and the share on total capacity will reach almost 70% in 2050. Other trend, electrification. We know that the demand of energy should decrease for the effect of energy efficiency, but the use of electricity as energy, as vehicle, is increasing. So finally, the electricity demand will increase, will double in 2050 compared to today's level. So it confirms that also according to important analysts of the energy sector, the relevance of electrification as main driver to decarbonize and to reach the transition. Next slide. So we have decarbonization, we said, the electrification, but also a decentralization of this generation. Why? It's been studied, in this case, the source is Bloomberg, New Energy Finance, that the size of plants of generation is going to be reduced. Okay, I think I'm showing all generation, so it's an average also with the conventional power plant. But it's clear that we are almost 1 gigawatt of median power plant size today. We are going to, with the introduction of more and more renewables that are smaller in terms of size, we are reaching 150 megawatt at the global level, even lower at the European level. Which is the first consequences of that, is that these plants are, as Silvia also said before, located where the renewable resources is, and very often closest to the consumption point, also in terms of distributed generation. And this generation is more and more connected directly to the distribution grid. Again, in the same report by Bloomberg, we find this estimation of a complete revert of the percentage between the share of capacity connected to transmission and the one connecting to distribution. So if today the one to distribution is only 24, it will reach almost 70% in 2050. Next slide, please. So, which is the final point on this view on scenario, the need to work on grids, okay? The need to reinforce that the grids, modernize and digitalize the network at all levels. Of course, investments are needed to do this kind of investment. And also in this case, consistently with the figures shown before, you see the amount of investment estimated by the IEA, and especially you see that from an expenses for grids today that was around $300 billion as average 2021. In the last decade, let's say, we will have an average expenses of 870 billion. Okay, so it's 3 times the investment foreseen today. Most of these are in the Asia Pacific area, also for the needs to really expand and create grids in some part. Africa would absorb 2% of this global investment in the IEA investment. But the important data, again, is that 60% of this amount will be addressed, should be addressed to digitalize and reinforce the distribution grids. Next slide. Exactly on digitalization, I want to show you this detail within the investment that exactly show what I was saying, that the share of digitalization, the investment devoted to digitalization is increasing from the current 13% on total CapEx today to about 40% by 2030. Okay, so it highlights again the need to work in creating grids that are be able to manage all the challenges that the energy transition is posing. So next slide. Let's think how should be these grids. Okay, in a sort of agenda, I would try to touch these 4 points to highlight in this context how the grids should evolve. So let's start with the resilience of the grids. Next slide. Resilience is a phenomenon I think very well known. It's we know that it's a consequence of the climate change as a consequence the increase in extreme weather events. This is a study from an insurance company that studied how in the last decades the events due to hydrological, climatological, geophysical, and chronic and acute events are increasing. And just to leave you with this figure, today more than 2 extreme events per day happen in the world. Remember that when we say extreme, we are talking about extraordinary events in terms of impact, so in terms of, for example, amount of rain, speed of the wind, and in terms of frequency. So it's these events are increasing as intensity and as a frequency. Please, next slide. It's clear in this sense that there is an urgency also from institution to fight this issue of extreme event and to ask for adaptation measure, not only at the public level, so at country level from institution, but it's also for the private company. Already in 2021, the European Commission asked for an integration of climate scenario in risk control. At the global level, World Economic Forum released a report underlying how and why the adaptation strategy are not only a matter of country, are a matter for all. And finally, in the assessment report in 2022 IPCC, that you know is the keynote authority in terms of climate change, studied the impact and the effect and the measure for adaptation from climate change. So also in the last COP27 in Sharm el-Sheikh has been defined some goal to be reached in terms of adaptation, an agenda with really action to fill the gap, especially in the most vulnerable country, because of course the extreme event have an even worse impact where there is an infrastructure and a context fragile. Next slide, please. Going more precisely, more better to the grids, just a few words on which are the events that more affect networks. We have the heat waves that consist in high temperature that last for several days and mainly are bad effect on underground cable. So it's important that the design of network or in the engineering phase already take into account the condition of this heat wave, try to prolong the life of the asset. Then there is the phenomenon of wet snow and ice slips that impact on aerial lines. It's a very special condition, very special combination of humidity, temperature, and impact on a specific typology of network. But it's very, very impacting. For example, also in Italy, it's one of the most frequent phenomena that cause interruption in the supply of energy. Fires, of course, it's a phenomenon that will increase with climate change, and it could be due to network itself. Do you remember probably the California events, very recent, or also Australia, and or linked to fire in the arid areas. So it's very important in this case, the vegetation management and the monitoring. Windstorm, so we have all the impact directly on the line or indirectly through the fall of a tree in case of area in out of urban area, and flood and rain, of course. Next slide, please. So how manage the resilience? So which is the adaptation measure that company, in this case, distribution company, can adopt? I bring here the example for ML grids that actually is one of the possible approach, and I also suggest this report that I mentioned in the bottom line by Euroelectric that collect the best practice in place by private company to increase the resilience of the infrastructures. So very quickly, we are talking of prevention, of course, so develop guideline methodology and make forecast and risk assessment. Readiness, how to be ready? Readiness means to be aware as soon as possible of the phenomenon. So have sensor control, automatic control and advanced sensorization that make you aware of the condition of your grid. Response, of course, so react promptly and manage, try to reduce the area of impact. It's the first action. So try to have grids as more meshed as possible in order to recover as soon as possible from the emergency. And the recovery exactly is also to access to other sources, not only the typical diesel generator to provide flexibility, to provide energy in case of emergency, but also rely on other flexible sources, on storage, on other tools. Next slide, please. Very quickly on sustainability, because we mentioned resilience, but don't forget that we are going to this trend, and to reach this transition as a just transition, we need to remember to have a fair and inclusive transition that leaves no one behind. So the sustainable approach should include also some grids and network included in an ecosystem. Next slide. And why? Because actually grids and the action, the strategy on grids impact on the goals for sustainability. We have the direct impact because for the energy access, so the SDG 7, so the access to all client, to all customer, and probably for Africa especially, this is one of the main goals to be reached. The innovation and new technology, because one of the mission of the distributor operator is to build resilient infrastructure and promote sustainable business model. Promote in cities and communities, of course, the fair development of the infrastructure and the energy system, and of course indirectly contribute to the reduction of CO2, even directly allowing the connection of renewables and also directly reducing losses on the grids. How to reach such goals? Of course, the key is work along the full value chain. So from designing, engineering, until the end life of the materials, and involving all the stakeholders. So from providers, from community, customer, and sharing best practice also with peers and other players. Next slide. At the beginning, I described pretty well the context. Silvia in the previous presentation very well focused on the challenges posed by variable renewable energy. So I think this representation should be pretty clear. The electricity system is evolving from one monodirectional flows from centralized generation to a bidirectional context in which we have more resources, more heterogeneous kind of sources on grids. We have active customer, and in this new context, the DSO expand its conventional scope. Next slide, please. To give some example, we should think to a DSO that is changing his main activity, well, not changing, it's increasing because it's continuing to distribute electricity, monitor consumption, of course, manage the network, but it's going beyond, because it needs to monitor and control also distributed generation connected to its grid, to coordinate with the other stakeholders. We mentioned the TSO before, but also customer and other flexibility service provider, as to enhance hosting capacity and guarantee hosting capacity to renewables, and as to manage and solve the local congestion or issue related to voltage regulation that can be more and more also due to the evolving characteristic of the electricity system, and need to plan the evolution of the grids, taking into account the availability of these sources of flexibility, always keeping in mind also the affordability and the cost for the system. How can we manage this interaction with flexibility? It's needed exactly to have some market for flexibility. Again, Silvia mentioned before the possibility for plants, for demand to provide services, but what is needed is to have some trading platform that can be used by network operators to procure, to buy these services, and use these services when needed to solve a problem in the grids, always guaranteeing the security of supply and the quality of service. So it's very important to procure the resources exactly in the point, so in a geographical limited area where there is a forecast for a problem, for a congestion, and with some characteristics. Here you have some example of product from the UK market that is the most developed one. They already in 2018 started to do tenders to procure flexibility products. The tender are technological neutral, so any distributed resources can participate. It's important to comply with the parameter set in the tender in terms of location. So the resources should be located and connected to a certain node in the grid, and in terms of availability, some products require a longer time to respond, so you can schedule and you can be ready, for example, in 30 minutes for a couple of products. Other products are more addressed to a real-time answer. Next slide. Actually, this is a very illustrative, very synthetic view of market deployment in terms of flexibility, because actually we are talking of of local flexibility. So don't think to ancillary services for TSO, but we are looking now to services for DSO. So they are much more defined in terms of location, and actually it's not a well developed market yet. It's completely under definition in some countries. For example, in Italy, in Spain, but also in other European countries, in Germany, have been done some experiment, some pilot project to test the possibility to buy and to use sources, to test also the coordination with the TSO. For example, in Netherlands, there is a platform that has already put in place this kind of coordination named GOVAX. But actually, as I said before, the only working market is the one in UK regarding Europe, and outside of Europe we have US and Australia also, even though in that case the typology of answer is and the typology of product are on a mid-term, is not really on a real-time base like in UK. However, this is something that needs to be developed, because it's something also foreseen by European Commission and by the Clean Energy Package, so it's completely under development. Next slide. We have touched different points: the resilience, the sustainability, the flexibility, which is which is the layer needed to really become resilient and flexible, to be digitalized. So digitalization is really the lever upon which DSO will ensure that this trend can really put in place. It's something that for some DSO is more advanced in other countries, in Latin America, also in Africa. It's something that is need to developed, that need to grow, but it's for sure the basic layer needed to pursue the other objective. Next slide. Just some example of the path in terms of the digitalization, because we can have some cluster, we can say. So we can think to digitalization in the sense of metering. So the smart meter for consumer, the metering also in the substation, for the generation, for the renewable generation. So all the advanced system to measure the flow on the grid. The other category is exactly the sensor and the automated remote control along the grid. So the issue of to be able to manage to operate on the grids from remote, from control room, and we saw before talking about resilience that it's very important and key when you have an emergency, when you have a problem with the continuity of service. It's very important, and it improves a lot the time of response, the possibility to act from remote on the grid. So advanced automation and remote control are probably the first category, together with the sensor. And finally, we have a category of digitalization that impact on field activities. So digitalization helps also to improve and to train people, to improve the way to work in terms of safety solution, in terms to train and simulate through augmented and virtual reality, in terms to replicate the grids. For example, the network digital twin is a way to have a copy, let's say digital copy of the grids, and allow to simulate before some problem, some impact. And finally, the use of drones and the robot drones also for the monitoring, for the issue of vegetation management, to verify the condition of the grids, and the robot also to replace the worker in a close future, in the near future, in the most dangerous activities. Next slide. Talking about the digitalization, I put here in the presentation just a couple of examples in the cluster I mentioned before. So the first one is related to smart meters. It seems to be a very easy device, but actually it really enable benefits and possibility for all the aspect of in the electricity system and for many stakeholders. So it's something that, especially in Italy, we see like something granted because everyone has the smart meter, but actually it's not the same in most parts of the world. Also in Europe, we have some countries that are behind in terms of development of smart meters. But of course, without smart meter, you cannot go the step beyond in the interaction with the customer, in the possibility to provide services from active consumer, from prosumers. So it's really the step needed to engage all these stakeholders. And the second example in the next slide, please. It's related to the secondary substation, so the substation for DSO from medium to low voltage. It's really emerge of a lot of technology, a lot of digitalization, from optic fiber for the communication, from system of automation for self-healing, from sensor, of course, but also something addressed to the design, so the civil work related to the substation that have to reduce, for example, the CO2 impact, and again the gas SF6 that is contained in the circuit breakers in the substation is something on which distributors are working, because it's a really high greenhouse gases. It's a greenhouse gases and needs to be replaced. So even doing a picture in a snapshot of the substation, you can find a lot of details, that a lot of innovation and technology that allow the distributor to really perform its role for the energy transition. I have finished with that. So next slide. And I hope this excursus on the main characteristic of DSO is clear, and so I really thank you for this possibility to this presentation for you, and the material will be available, of course. Thank you very much.
Thank you, Mena Testa, and thank you for presenting us the point of view of one of the most important DSO in the world, about the new grids of the future, that I would resume in a nutshell as with a few slogans. So the new grids has to be resilient, sustainable, and flexible, and thanks mainly to digitalization. That is the key to reach this goal, I would say.
Thank you very much for that.
Thank you again. And now it's the moment of the last speaker, Dario Impala, that is responsible inside RES4Africa for the Grids for Africa program. And so he will tell us which is the relevant point of view of RES4Africa regarding this the topic of today. So Dario, please, the floor is yours.
Thanks, Fabrizio. Good morning, everyone. Next slide, please. Today, I want to share with you what is the actual state of Africa network infrastructure and what Grids for Africa is in terms of scope, tools, and activities of the program. Next slide, please. As you well know, one of the main challenges that Africa is facing regards to the access to electricity, which level is very low, and we're talking about 40%, so it means in other terms that more than half Africans has no access to electricity. And if we consider the main representative African countries by area in the chart, we can notice that it's easier to find an access to electricity equal to 100% in the North Africa, in countries such as Algeria and Morocco, and it's most difficult to find it in sub-Saharan countries such as Zambia and Tanzania. Same stories regarding the electricity consumption per capita, where the higher level is found in South Africa, and the lowest one is in Uganda and Ethiopia, for example. But the main important things to underline is that the higher level of consumption per capita in Africa is equal to 4 megawatt-hour per year. That is still far away a level from the data that we are well know about the most industrialization countries such as the United States, for example, whose level is 11 megawatt-hour per capita, or Germany, for example, whose level is 6 megawatt-hour per capita. Next slide, please. About the quality of service, we have to say that the quality is always too low. And if we consider the same sample of countries, Uganda and Ghana, for example, are the lowest the level of SAIDI and SAIFI, where SAIDI and SAIFI are the main representative KPI for power supply And the first one, Saidi, gives us an idea of the duration of interruption during a year. And the second one gives us an idea of the frequency of the interruption in terms of number of interruption per year. Unlike Morocco, in North Africa, is the unique country where the satiety and safety level is better than the world average, that is equal to 3. Next slide, please. What I've seen so far is a strict consequence of the lack of the infrastructure in the region. What we used to say the African iron problem. In fact, if we compare, just to give you an idea of the level of infrastructure that we have today in Africa, if we compare a surface that is quite similar to Africa in terms of million of kilometers and population, that is America, both in terms of absolute value, or that is length of transmission, and in density, that is a kilometer per million people, we can notice that the level of the American development networks is 4 times the African one. That means, in other terms, that the African level development of network is still so far from the level that we know. Next slide, please. One of the main bottlenecks is represented by the regulation framework. If we consider the sample of our studies, only 4 countries, that are Morocco, Ghana, Zambia, and Uganda, as private distribution companies, and only Zambia has a private sector participation in all 3 segments. But it's important to underline that it's not necessary to have an unbundling process to have the private sector participation, and above all, it's more important to say that the successful private sector participation that we have seen in generations so far in Africa is also replicated in transmission distribution sector too. Next slide, please. Lack of regulation means lack of uncertainty. That means, in other terms, lack of investment. If we consider, in fact, the last private sector investment during the last decade in Africa and the rest of the world, the percentage relates to Africa is just 10%. This 10% is almost refers to renewables generation, and when we talk private investment sector in Greece, we refer to just to 0.3%, so crowns. Next slide, please. The scarcity of investment creates what we used to call the utility vicious cycle. A cycle with a negative aspect due to the fact that the regulators in most cases set not in a proper way the tariff that can cover the investment in the long term, that we can call capex, but only the investment in the short term. So it means that there's no money for important investment such as transmission, distribution, to create new ones or to reinforce the previous dam, the previous transmission line that are already in place. And for this reason, the service quality is eroded, and a lot of customer is considered allowed to stop paying billing. So this is create again the lack of money for more utilities, and the cycle starts again. A vicious cycle that is very tough to break out. Next slide, please. The lack of investment means not only a problem for the single company or utility, but also a huge problem for every single African country, such as, for example, South Africa. Because it's a typical phenomenon of the country of the last years that is accumulated blackout, or called load shedding. It's a phenomenon that is increasing in the last 4 years. As you can see in the chart, by the first week of the May, South Africa has already reached the level of the previous year. But the most important thing to point out here is that there's an impact on, from an economical point of view, that is equal to 5% of the GDP lost during the 2022 in South Africa. Or in other terms, as you can see from the chart, for sure the level for 2023 will surpass, will overcome the level of 2002 with a more negative effect that South Africa has to face in 2023. Next slide, please. Where there's a lack of regulation on investment, interconnection could give an help, but we in Africa are in the first stage. Just to give you an idea, we prepared a comparison between Germany and then Africa. And although the surface of Germany is more or less 10 times smaller than Africa, in terms of absolute value, we have more or less the same level of total connection that is equal 20 gigawatts. Sorry, but it means if we're talking about the import-export power volume, that the volume we can notice that the level of the Germany is double than the Africa one. So it means that, next slide please, the power market in Africa is also in the first stage or under construction. We divided the 5 African power pool by the development degree, and we can notice that only South and West African power pool can be considered at the middle high level of development degree, due to mainly to trading platform and the balancing mechanism that can be considered at a good level of development with the uniform presence of regulators too. About the last 3 African power pool, the level of development can be considered very low, and it's important to notice the contradiction of the COMELEC, the north part of South Africa, where there's the presence of the higher level of access to electricity, the good level of the infrastructure, but although this, there's not the willingness so far of the local stakeholders to create a real and effective common market with stable trading platform and balancing mechanism. Next slide, please. So what we've seen so far, the balance of the African energy sector, because it is characterized by population urbanization growth, more reliable demand of power infrastructure, and more infrastructure needs. That these 3 elements represent an opportunity, but at the same time in Africa represent a risk. And how is it possible to switch this opportunity, this risk in opportunities? Next slide, please. First of all, it's important the more presence of private participation in the sector. In the chart, you can notice that where there's a presence of private, there's from a technical economical point of view, good performance, and the private utilities does better the public one. Next slide, please. But it's also important to create the good regulator condition with the effective and cost-reflective tariff reform that so far is applied or under discussion just only in African countries. And based on studies, it's important to underline that if all countries applied a cost-reflective tariff reform, there will be savings for 70% of costs. Operational cost, that's a huge amount. Next slide, please. Private sector participation, it's possible also, and it's important to mitigate the risk. In fact, in the chart, we can see that there are a lot of agreement based on the risk and time sharing that goes from service contract to the divested merchant project. In the first case, we have the risk that all managed by public, and in the last part of the chart we have the divested and merchant project that there are agreement where private manage all the risk for indefinite time. In the middle we have the public-private partnership with the 3 agreements that are the management contract, the lease agreement, and the concession, divided based on the degree of the involvement and the management of risk by private and public. Next slide, please. The important presence of the private sector is necessary also to fill the investment gap that the region is requiring to reach the main goals that Africa is setting out by 2033. In fact, based on a study of International Energy Agency, based also on a sustainable Africa scenario, to reach a decrease of the network loss by 5% point, for example, as you can see in the chart on right, it's necessary to increase the investment on grid from the actual 10 billion to 40 billion of dollars, a huge amount, and most of this is required for the construction of new lines. Next slide, please. So private sector participation is most important because due to the fact that the financial Africa scenario is worsening in the last 3 years. If we consider the total amount of debt of the African countries on the GDP, we can notice that the ratio is double. So it means in other terms that the financial condition of main African country is worsening. In fact, more or less 20 countries are bankrupt in Africa or at high risk of debt distress. Next slide, please. Among the agreement in the public-private sector that we have seen so far, one of them is the concession model called independent power transmission. That is one of the best solutions that private and public can choose, because it's a single, replicate for a single small number of transmission, quite similar to PPA in the renewable sector. It's awarded through tenders in order to identify the lower price, and also in this kind of contract, it's possible to fix at the beginning of the contracts the O&M cost that is locked. So it's another way to manage in the best way the risk in the agreement, and can be replaced alongside existing grid without impact it. For this reason, the independent power transmission can be considered a successful concession model that it has introduced in regional such as LATAM, in the specific countries, as you can see in the chart, that are Peru, Chile, and Brazil. Next slide, please. So it's possible to replicate and consider the independent power transmission such as a successful model in Africa. We can see that is possible, that is the way, and we are not alone to think that, because Kenya and Uganda, for example, has already signed two kinds of independent power transmission. In particular, in Kenya, the public company of transmission called KETRACO signs an agreement with Africa 15 Power Grid for the construction of 300 kilometers for more or less 300 million of investment, where all risk are borne by the private company. And a quite similar contract is signed by the government of Uganda and Gridworks for the construction on brownfield substation for an amount of now 90 million of equity fundings. Next slide, please. So what we have seen so far is divided into two phases. The first stage of our presentation that relate to the main challenges of African region is facing, and the second one that represent or illustrates the main instruments that local stakeholders can adopt to try to stop the balance that we noticed so far, that are represented by the better regulation and the more private sector participation. In the middle, we pose for a joke RES4AFRICA Foundation program dedicated to the development of grids that is called Grids for Africa. Next slide, please. Which purpose is to raise awareness about the importance of grid infrastructure and to support the development of public-private partnership to attract and to raise the investment necessary to create more condition and more development of grids and transmission lines in the region. What are the activities that the program is using? The stakeholder engagement, first of all, we then the strategic analysis and knowledge dissemination, and finally we have the group, the training program that are strictly focused on grid and storage. Next slide, please. So you can find the main activities carried out to date by the program. With a great successful we had a program, Grid and Storage Lab in Morocco. We prepared some specific studies such as private sector participation in African grid development. We create event and position paper also in other important countries in the sub-Saharan region of Africa, such as Kenya. Next slide, please. Finally, we have the Grids Africa next step. In particular, about Grid and Storage Lab, we have a training that on behalf of KPLC to realize in the first part of July. By the end of the year, we have the opportunity to collaborate with ESCOM to create some specific grid storage lab also. And on the 9th of June in Nairobi, we have the second part of the Development Partners Forum, that is a closed workshop to discuss best practice and to how to promote private sector participation. And finally, on table, we have 3 ongoing reports and studies, of which 2 are already started. The first one relates to the transmission distribution tariff definition. The second one regards the frequent digital solution, and the third that will start in the second part of the year relates to urban and peri-urban studies. So I finished. I hope you enjoyed the presentation. You understood well what are the challenge that the African region is facing on network development, the importance of the instrument that Grids for Africa is carrying out so far, and also the foundation. So many thanks, and see you soon.
Thank you, Dario. Thank you for having provided us this complete overview on the African situation regarding the grid infrastructures, and thank you also for having provided which are the programs related to grids in Grids for Africa, in RES4AFRICA Foundation. So thank you, and we are at the end of this session. I just want to remember you that the next session will be on June 7, and it will be dedicated to another important brick of the entire picture, that is the green hydrogen. What is the green hydrogen, and which is the role of green hydrogen in a sustainable development of African continent. So I'm sure that you will be participating also to the next session. And for the moment, I really thank you, everybody. I thank all the organizers and all the speakers for the excellent webinar, and so see you on June 7.